What's up, everyone? Today we're going to talk about the chi-squared goodness of fit test, so let's get into it. So a bit of information about the test before we actually do it. The chi-squared goodness of fit test is used when you have one nominal variable with two or more values. And what we mean by nominal variable is one that has no order or number associated with it. So like your eye color, the blood type, zip code. So similar to a qualitative piece of data. In a chi-square goodness of fit test, the number of degrees of freedom is just n minus 1. When we looked at the test for independence, we had a whole table where we were comparing two different values. So it was the number of rows minus 1 times the number of columns minus 1. In the goodness of fit test, we're looking at just one single variable. So the degrees of freedom, we're just taking how many total values we have and subtracting 1. So the goodness of fit test works very similarly to our test for independence, except besides the degrees of freedom being a little bit different. The null hypothesis itself, there is still a null hypothesis, but instead of that, the two variables you're looking at are independent. We're just going to say that they will follow what we might predict. Usually they'll tell you in the problem what they're looking for. So like they're equally likely, they're normally distributed, which we're going to talk more about in our last unit. They satisfy a uniform distribution, something that you would just expect to happen anyway. The other piece of difference is that in your graphic display calculator, instead of inputting the values into a matrix, so again, because we would have a whole table in our test for independence, when we only have one single value, we're going to take those values and we're going to put them in a list and then obviously choose the goodness of fit test. All right, so in this document, which I'll link below, is how to find the goodness of fit calculated value in your calculator, both with the older versions of the TI and with the newer versions. So let's get into an example. 105 students in year 8 were asked what day of the week their birthdays were on this year, and the table below shows the results. So again, very similar to our test for independence, these are our observed values, the ones that are given to us. In part A, we're asked to write down the table of expected values, given that each day is equally likely. So again, they're telling us what we're expecting to expect. All right, so they're saying if each day is equally likely, that means I have 7 total days. I also know that I have 105 total students. So 105 divided by the 7 days means that on each day, it should be 15. So if it's an equally likely scenario like this one, your expected values will have the same value for every single piece, in this case, for every single day. Calculate part B, calculate a goodness of fit test at the 5% significance level for this data. So they're telling us in the parentheses what all that entails. We need to state our null hypothesis first. So again, our null hypothesis is that each day is equally likely. Also need to state my alternative hypothesis. Just like our chi-squared test for independence, your alternative hypothesis is exactly what your null said, except is not equally likely in this case. So next up, they want us to write out the degrees of freedom. So my V or DF, either way. I'm taking the total number of values I have, which is 7 since it's the days of the week, minus 1. So my degrees of freedom, or the number of degrees of freedom I have, is 6. The calculated value and the p-value, again, are going to come from our calculator. So in my calculator, I'm going to go into my lists, and this is all in that document from the previous slide, and edit. I'm going to make one list for my observed values and one list for my expected values. From there, I'll run the test. I'll go back into stat, over to tests, and down to letter D with goodness of fit test. Keeping in mind that if you have just the 83 or maybe even the 84 not plus, the directions are going to look a little bit different. But again, I linked those in the other document. So I'll run my test. My observed is in L1, my expected is in L2. I do need to know my degrees of freedom for this before I can run the test. So unlike the test for independence, you do need to know the degrees of freedom going into this and change it accordingly on this page before you calculate it. So once I calculate it out, it gives me the chi-squared value, which is 1.6. It gives me the p-value, which in this case is 0.953. Gives you the degrees of freedom, even though you gave it to it. This final piece on the bottom, if you hit the right arrow, you can see all of them. That gives you that chi-squared calculated value for each individual value. Just like we saw for the test for independence, it's taking the observed value minus the expected value squared and divided by the expected value. So it's just giving you all of those pieces, just in case you need them, I guess. So my chi-squared value is 1.6. My p-value is 0.953. All right, and finally in part C, they're giving us the critical value is 12.592, and we're writing down the conclusion for the test. The nice thing is making that conclusion is the exact same as it was for the test for independence. If the calculated value is less than the critical, I accept. If the p-value is greater than the significance level, I accept, and then the opposite for rejecting. So let me set up my inequalities. So looking at my calc and critical values, my calculated value is less than my critical value. Looking at my p-value versus my significance level, my p-value is greater than my significance level. So again, my inequality signs are facing each other, so they're accepting each other, and I'm accepting my null hypothesis, meaning that each day is equally likely. All right, one more example. Zhang wonders whether the die he was given is fair. He rolls it 300 times, and his results are shown in this table at the right. So these are our observed values. In part A, we're asked to write down the expected values, assuming each number is equally likely. So especially since we haven't gotten into a lot of the probability yet, we're going to strategically choose a lot of problems that just assume each number is equally likely. And once we get into probability, depending on how much time we have left at the end of the year, we'll get into other types, but just know that, with normally distributed values, stuff like that, we're not going to choose those yet because we haven't had a chance to talk about them yet. But we're assuming each value here is equally likely. He rolls it 300 times. So very similar to our days of the week. Since I have 6 values here for my 6 sides of the die, I'm going to divide that 300 by 6, and I'm going to get that each side is, the frequency would be 50. So again, if it's equally likely, same frequency all the way through the table. Part B, we're calculating a chi-square goodness of fit test at the 5% significance level for this data. So again, it gives us all the pieces of the puzzle. So let's run through them. My null hypothesis is that in this case, each side of the die is equally likely. For my alternative hypothesis, again, same as my null, except each side of the die is not equally likely. My degrees of freedom, and I can go back if I need to, or you can. I know I have 6 sides of the die, so my degrees of freedom would be 6 minus 1 would be 5. So V or DF, you can write out 6 minus 1, or since it's just simple subtraction, you can also just write out the 5. Doing the calculated value, I'm going to open up my calculator into Stat and Edit. You can clear them out or leave them in. I'm putting in my frequencies into L1 because this one has the number on the side of the die. It looks like you might want to do that too, but you don't. Remember, that's what we're looking at. Just like with the days of the week, that's the equivalent of the days of the week in this problem. My expected frequencies was 50. Running my test, stat, test, goodness of fit test. L1, L2, my degrees of freedom now is 5. So then I'll go down to calculate. So I've copied over my calculated value is 22.24. My p-value, it is 4.71 times 10 to that negative fourth. It did have the e at the end. Or in standard form, 0.000471. So writing down my conclusion for the test, if you noticed in this problem, whether it's on this page where they do give us the significance level or the previous page, they don't give us a critical value. So that means I have to use the p-value and the significance level to compare. So I'm looking at my p-value and my significance level. Again, I always put them into decimals. If it helps, if it makes it a little bit easier, you can bring that p-value up to a percentage and compare, in this case, 0.0471 and 5% and do it that way. If the decimals, depending on how small they get, if that makes it easier. But either way, I'm looking at my p-value being less than my significance level. So even though I don't have my critical value in order to use my chi-squared values as well, I can still picture it over here, right? That if my p-value is less than my significance level, that would mean if I was giving my critical value, my inequalities are facing away from each other. That means I am rejecting my null hypothesis. So we would be saying in this case, my null hypothesis was that each side is equally likely, so each side is not equally likely in this case.